Section 11.2, Intermolecular Forces. The strengths of intermolecular forces of different substances vary over a wide range, but are generally much weaker than ionic or covalent bonds. Less energy, therefore, is required to vaporize or evaporate a liquid or to melt a solid than to break the covalent bonds in molecules. For example, only 16 kilojoules per mole is required to overcome the intermolecular attractions between hydrochloric acid molecules in liquid hydrochloric acid to vaporize it. In contrast, the energy required to break the covalent bonds to dissociate hydrogen chloride into hydrogen chlorine atoms is 431 kilojoules per mole. Thus, when a molecular substance such as hydrochloric acid changes from solid to liquid to gas, the molecules themselves remain intact. Many properties of liquids, including their boiling points, reflects the strengths of the intermolecular forces. For example, because the forces between hydrochloric acid molecules are so weak, hydrochloric acid boils at a very low temperature, negative 85 Celsius at atmospheric pressure. A liquid boils when bubbles of its vapor form within the liquid. Figure 11.2, Intermolecular Attraction. Comparison of a covalent bond, an intramolecular force, and an intermolecular attraction. Because intermolecular attractions are weaker than covalent bonds, they're usually represented by dashes or dots. The molecules of a liquid must overcome their attractive forces to separate and form a vapor. The stronger the attractive forces are, the higher the temperature at which a liquid boils. Similarly, the melting points of solids increase as the strengths of the intermolecular forces increase. Three types of intermolecular attractions exist between neutral molecules: dipole-dipole attractions, London dispersion forces, and hydrogen bonding. The first two forms of attraction are collectively called van der Waals forces, after Johannes van der Waals, who developed the equation for predicting the deviation of gases from ideal behavior. Another kind of attractive force, the ion-dipole force, is important in solutions. All of these intermolecular attractions are electrostatic in nature, involving attractions between positive and negative species. Even at their strongest, these interactions are much weaker than covalent or ionic bonding, about 15% or less as strong. Ion-dipole forces. An ion-dipole force exists between an ion and the partial charge on the end of a polar molecule. Polar molecules are dipoles. They have a positive end and a negative end. Hydrochloric acid is a polar molecule, for example, because the electronegativities of hydrogen and chlorine atoms differ. Positive ions are attracted to the negative end of the dipole, whereas negative ions are attracted to the positive end, as shown in Figure 11.3. The magnitude of the attraction increases as either the charge of the ion or the magnitude of the dipole moment increases. Ion-dipole forces are especially important for solutions of ionic substances in polar liquid, such as a solution of sodium chloride in water. We'll discuss these solutions more in detail in Section 13.1. Figure 11.3, Ion-dipole attractions. Illustration of the preferred orientations of polar molecules towards ions. The negative end of the dipole is oriented towards the cation, and the positive end of the dipole is oriented towards the anion. Dipole-dipole forces. Neutral polar molecules attract each other when the positive end of one molecule is near the negative end of another, as shown in 11.4. These dipole-dipole forces are effective only when polar molecules are very close together. Dipole-dipole forces are generally weaker than ion-dipole forces. In liquids, polar molecules are free to move with respect to one another. As shown in Figure 11.4, the polar molecules will sometimes be in an orientation that is attractive, red solid lines, but sometimes in orientation that's repulsive, blue dashed lines. Two molecules that are attracting each other spend more time near each other than do those that are repelling each other. Thus, the overall effect is a net attraction. When we examine various liquids, we find that for molecules of approximately equal mass and size, the strength of intermolecular attractions increase with increasing polarity. We can see this trend in Table 11.2, which lists several substances with similar molecular weights but different dipole moments. Notice that the boiling point increases as the dipole moment increases. For dipole-dipole forces to operate, the molecules must be able to get into close together in the correct orientation. Figure 11.4, Dipole-Dipole Attractions. The interaction of many dipoles in a condensed state. There are both repulsive interactions between like charges and attractive interactions between unlike charges, but the attractive interactions predominate. For molecules of comparative polarity, therefore, those with smaller molecular volumes generally experience higher dipole-dipole attractive forces. London dispersion forces. No dipole-dipole forces exist between nonpolar atoms and molecules because nonpolar atoms, molecules, and atoms do not have a dipole moment. Some kind of attractive interactions exist, however, because nonpolar gases such as helium and argon can be liquefied. Fritz London, a German-American physicist, first proposed the origin of attraction in 1930. London recognized that the motion of electrons in an atom or molecule can create an instantaneous or momentary dipole moment. In a collection of helium atoms, for example, the average distribution of electrons about the nucleus is spherically symmetrical. The atoms are nonpolar and possess no permanent dipole moment. The instantaneous distribution of the electrons, however, can be different from the average distribution. If we could freeze the motion of electrons in a helium at any given instant, both electrons could be on one side of the nucleus. At just that instant, then, the atoms would have an instantaneous dipole moment. The motions of electrons on one atom influences the motions of electrons on their neighbor. The temporary dipole in one can induce a similar temporary dipole in an adjacent atom, causing the atoms to be attracted together, as shown in Figure 11.5. This attractive interaction is called a London dispersion force, or merely a dispersion force. The dispersion force, like dipole-dipole forces, are significant only when molecules are very close together. The strength of the dispersion force depends on the ease with which the charge distribution in the molecule can be distorted to induce momentary dipole. The ease with which the electron distribution in a molecule is distorted is called its polarizability. We can think of polarizability of a molecule as the measure of its squashiness of its electron cloud. The greater the polarizability of the molecule, the more easily the electron cloud can be distorted to give momentary dipole. Therefore, more polarizable molecules have larger dispersion forces. Figure 11.5, Dispersion Forces. On the average, the charge distribution in the helium atoms is spherical, as represented by the spheres in A. At particular instant, however, there can be a non-spherical arrangement of the electrons as indicated by the location of the electron in A and by the non-spherical shape of the electron cloud in B. The non-spherical electron distribution produces momentary dipoles and allow momentary electrostatic attractions between atoms that are called London dispersion forces or merely dispersion forces. In general, larger molecules tend to have greater polarizabilities because they have greater number of electrons, and their electrons are farther from the nuclei. The strength of dispersion forces, therefore, tend to increase with increasing atomic or molecular size. Because molecular size and mass generally parallel each other, dispersion forces tend to increase in strength with increasing molecular weight. Thus, the boiling points of the halogens and the noble gases increase with increasing molecular weight. The shapes of molecules also influence the magnitudes of dispersion forces. For example, N-pentane and neopentane illustrated in Figure 11.6 have the same molecular formula, yet the boiling point of N-pentane is 27 Kelvin higher than that of neopentane. The difference can be traced to the different shapes of the two molecules. The overall attraction between molecules is greater for N-pentane because the molecules can become in contact over the entire length of the long, somewhat cylindrically shaped molecule. Less contact is possible between the more compact and nearly spherical molecules of neopentane. Dispersion forces operate between all molecules, whether they're polar or nonpolar. Polar molecules experience dipole-dipole interactions, but also experience dispersion forces at the same time. In fact, dispersion forces between polar molecules commonly contribute more to the intermolecular attraction than to dipole-dipole forces. In liquid hydrochloric acid, for example, dispersion forces are estimated to account for more than 80% of the total attraction between molecules. Dipole-dipole attractions account for the rest. When comparing the relative strengths of intermolecular attractions in two substances, consider the following generalizations. 1. when the molecules of two substances have comparable molecular weights and shapes. Dispersion forces are approximately equal in the two substances. In this case, differences in magnitudes of the attractive forces are due to differences in the strengths of dipole-dipole attractions, with more polar molecules having the stronger attractions. 2. When the molecules of two substances differ widely in molecular weights, dispersion forces tend to be decisive in determining which substance has the stronger intermolecular attractions. In this case, differences in the magnitude of the attractive forces can usually be associated with differences in molecular weights, with the substances made up more massive molecule having the strongest attractions, assuming similar dipole moments. The hydrogen bond, which we'll consider after sample 11.1, is a special type of dipole-dipole attraction that's typically stronger than dispersion forces. Hydrogen bonding. Figure 11.7 shows that the boiling points of a simple hydrogen compounds of group 4A and 6A elements. In general, the boiling point increases with increasing molecular weight, owing to the increased dispersion forces. The notable exception to this trend is water, whose boiling point is much higher than we would expect because of its molecular weight. This observation indicates that there are stronger intermolecular attractions between water molecules than are between the molecules of the same group. The compounds of ammonia and hydrofluoric acid likewise have abnormally high boiling points. In fact, these compounds have many characteristics that distinguish them from other substances of similar molecular weight and polarity. For example, water has a high melting point, a high specific heat, and a high heat of vaporization. Each of these properties indicates that the intermolecular forces between water molecules are abnormally strong. The strong intermolecular attraction in water results from hydrogen bonding. Hydrogen bonding is a special type of intermolecular attraction between the hydrogen atom in a polar bond, particularly hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen bond, and non-bonding electron pair in a very small electronegative ion or atom, usually a fluorine, oxygen, or nitrogen atom in another molecule. For example, hydrogen bond exists between hydrogen atoms in a hydrogen fluoride molecule and the fluorine atom of an adjacent hydrogen fluoride molecule, where the dots represent the hydrogen bond between the molecules. Several additional examples are shown in Figure 11.8. Figure 11.8, examples of hydrogen bonding. The solid lines represent covalent bonds. The red dotted lines represent hydrogen bonds. Hydrogen bonds can be considered unique dipole-dipole attractions because fluorine, nitrogen, and oxygen are so electronegative. A bond between hydrogen and any of these three elements is quite polar, and hydrogen at the positive end. The hydrogen atom has no inner core of electrons. Thus, the positive side of the bond dipole has a concentrated charge of the partially exposed, nearly bare proton of the hydrogen nucleus. This positive charge is attracted to the negative charge of the electronegative atom in a nearby molecule. Because the electron-poor hydrogen is so small, it can approach the electronegative atom very closely and thus interact strongly with it. The energies of the hydrogen bonds vary from about 5 kilojoules per mole to 25 kilojoules per mole or so, although there are isolated examples of hydrogen bond energies that are close to 100 kilojoules per mole. Thus, hydrogen bonds are typically much weaker than ordinary chemical bonds, which have bond energies of 200 to 1100 kilojoules per mole. Nevertheless, because hydrogen bonds are generally stronger than dipole-dipole or dispersion forces, they play important roles in many chemical systems, including those of biological significance. For example, hydrogen bonds help stabilize the structures of protein, which are key parts of skin, muscle, and other structure components of animal tissues. They're also responsible for the way that DNA is able to carry genetic information. One of the remarkable consequences of hydrogen bonding is found when the densities of ice and liquid water are compared. In most substances, the molecule of the solid is more densely packed than that of the liquid, thus the solid phase is denser than the liquid phase. By contrast, the density of ice at zero is less than that of liquid water, so ice floats on liquid water. The lower density of ice compared to that of water can be understood in terms of hydrogen bonding interactions between water molecules. The ice, the water molecules assume an ordered open arrangement as shown in figure 1110. This arrangement optimizes the hydrogen bonding interactions between the molecules, with the water forming hydrogen bonds to 4 other water molecules. These hydrogen bonds, however, create open cavities shown in the structure. When the ice melts, the motions of the molecules cause the structure to collapse. The hydrogen bonding in the liquid is more random than that of the ice, but strong enough to hold the molecules close together. Consequently, liquid water has a more dense structure than ice, meaning that the given mass of water occupies a smaller volume than the same mass of ice. Figure 1110, hydrogen bonding in ice. A, the hexagonal shape is characteristic of snowflakes. The arrangement of water molecules in ice. Each hydrogen atom of one water molecule is oriented towards a non-bonding pair of electrons of an adjacent water molecule. As a result, ice has an open hexagonal arrangement of water molecules. Hydrogen bonding between 2 water molecules, the distance shown, are those found in ice. The lower density of ice compared to liquid water profoundly affects life on Earth. Because ice floats, it covers the top of water when a lake freezes in cold weather, thereby insulating the water below. If ice were more dense than water, ice forming on the top of a lake would sink to the bottom and the lake would freeze solid. Most aquatic life could not survive under these conditions. The expansion of water upon freezing also is what causes pipes to break in freezing weather. Comparing intermolecular forces. We can identify the intermolecular forces that are operative in substance by considering its composition and structure. Dispersion forces are found in all substances. The strength of these attractions increase with increasing molecular weight and depend on molecular shapes. Dipole-dipole forces add to the effect of dispersion forces that are found in polar molecules. Hydrogen bonds, which require hydrogen atoms bonded to fluorine, oxygen, nitrogen, also add to the effect of dispersion forces. Hydrogen bonds tend to be the strongest type of intermolecular attraction. None of these intermolecular attractions, however, are as strong as an ordinary ionic or covalent bonds. In general, energies associated with dispersion forces and dipole-dipole forces are in the range of 2 to 10 kilojoules per mole, while the energies of hydrogen bonds are in the range for 5 to 25 kilojoules per mole. Ion dipole attractions lead to energies approximately 15 kilojoules per mole. It's important to realize that the effects of all these attractions are additive. For example, if a pair of molecules can make one hydrogen bond between them, but a second pair can make 3 equivalent hydrogen bonds between them, the second pair of molecules will be held with triple the energy of the first pair. Likewise, very large polar molecules such as proteins, which have multiple dipoles over their surfaces, can be held together in a solution to a surprisingly high degree by multiple dipole attractions. Figure 1112 represents a systematic way of identifying the kinds of intermolecular forces in a particular system, including ion-dipole and ion-ion forces. Figure 1112, flowchart for determining intermolecular forces. London dispersion forces occur in all instances. The strength of the other forces generally increase proceeding from left to right across the chart.